Here is something that looks wrong the first time you see it. The nth root of n. As n grows bigger and bigger, towards infinity. What does this expression approach? You might think, well, n is getting huge, so the nth root of n should also keep growing, right? But it does not. It approaches 1, the nth root of n, as n tends to infinity, equals exactly 1. Today we are going to prove this, rigorously, step by step, and by the end you will see exactly why this result is true. The key move in this proof is a clever substitution. We write the nth root of n as 1 plus alpha n. Here alpha n is some quantity that we do not know yet, but notice, we are claiming that the nth root of n is always slightly bigger than 1 for n greater than 1. So alpha n is positive and greater than 0. And our goal is to show that as n tends to infinity, alpha n tends to 0, because that would mean the nth root of n tends to 1 plus 0, which is 1. Now if the nth root of n equals 1 plus alpha n, then raising both sides to the power n gives us n equals 1 plus alpha n, all raised to the power n, where n is greater than 1. Now we expand the right side using the binomial theorem. N equals 1 plus m times alpha n plus n times n minus 1 over 2 factorial times alpha n squared, plus more terms, all the way up to alpha n to the power n. Since all terms are positive, we can drop the higher terms and write a simpler inequality. N is greater than 1 plus n times n minus 1 over 2 factorial times alpha n squared. Now let us simplify this step by step. We have n is greater than 1 plus n times n minus 1 over 2 factorial times alpha n squared. Subtract 1 from both sides. N minus 1 is greater than n times n minus 1 over 2 factorial times alpha n squared. Now divide both sides by n minus 1. Since n is greater than 1, n minus 1 is positive, so the inequality direction stays the same. This gives us 1 is greater than n over 2 factorial times alpha n squared. So we Now look at what we have. Alpha n is sandwiched between two values. Square root of 2 over n is greater than alpha n, which is greater than 0. Now we take the limit as n tends to infinity on both sides. The limit of the square root of 2 over n as n tends to infinity equals 0. And alpha n is always greater than 0. So by the squeeze theorem, alpha n is trapped between 0 and something that goes to 0. Therefore the limit of Now we finish the proof. We showed that the limit of alpha n as n tends to infinity equals 0. And we defined the nth root of n as 1 plus alpha n. So the limit as n tends to infinity of the nth root of n equals 1 plus the limit of alpha n as n tends to infinity, which equals 1 plus 0, which equals 1. The limit as n tends to infinity of the nth root of n equals 1. Proved. What made this proof work was one smart substitution at the start. Writing the nth root of n as 1 plus alpha n gave us something to squeeze, and the binomial theorem did the rest. This is the kind of elegant argument that shows up again and again in real analysis. If you found this helpful, like the video and subscribe for more proofs like this. Drop a comment if you want me to cover more limit proofs. See you in the next one.